So this question involves gravitational field strength between two objects. All right, so this is an old question, and normally in the gravitation chapter, most of the time we study fields and potential of one object. But this is an old question, and sometimes they do ask two objects. So let's check out this question first. Part A, you are asked to define gravitational field strength. So gravitational field strength here is defined as gravitational force per unit mass. Okay, the word gravitational is optional, but you should think of force per unit mass. Okay, so you are using the equation G is F over M, or F is equal to mg, your weight. Part B, an isolated star has a radius r, and the mass of the star may be considered to be a point mass at the center. Okay, so I think sometimes we tend to forget that all our gravitation assumption is assuming that it is a point mass, so that it's easy to do the calculation and we can apply Newton's law without calculation. Okay, so just remember that when you are defining Newton's law of gravity. Okay, so let's say this is a circle, okay, and all the mass is concentrated in the middle. Let's say this is M. Gravitational field strength at the surface of the star is GS, meaning at this point here, the gravitational field strength is GS. Okay, on this graph grid, sketch a graph to show the variation of gravitational field strength of star with distance from the center. So if we are measuring distance from the center, it means at the surface, we are talking about radius. Okay, so here to here is R, radius. All right, so that means okay, hang on, radius is capital R, right? It says here, blah, 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 radius R. Okay, so this is capital R. Meaning when the distance is r on the surface of the star, if you look at this thing here, okay, surface of the star, the value is GS, 1 GS. Okay, so then you should consider distances from r to 4r. Okay, so it's time to do some maths. Let's think about gravitational field strength. The equation of gravitational field strength is equal to gm over r square. But also at the same time, your r is the one that is changing. The mass of the sun is fairly constant, okay? So from here, what I have is g is inversely proportional to 1 over r square. So this means when your gravity, your radius times 2, your gravity will become less, okay? So I will write down that working for you if you need it. So normally, if you cannot, I suggest to build a table lah, okay? So let's say you're talking about R. When R is R, this is GS, okay? When this is R over 2, this will be, sorry, not R over 2, my bad, 2R, twice the radius, okay? So this will be GS over 4, or GS over 2 square. The further you are, the weaker it is, ma. All right, when it's 3r, then this will be GS over 9. Okay, use your ratios to help you. So hopefully by now you are clear with this. When it's 4r, this will be GS over 16. All right, so we are talking about 1 over the factor. Okay, so just in case you want to look at it, this one, when this is times 2, when you move from here to here, you times 1 over 2 square. Okay, so this is what I mean by inversely proportional lah. Okay, then you times 3 times 1 over 3 square. Okay, can? So now let's plot the graph. GS over 4 is 0.25. So where is our 0.25? 0.25, okay, I need to change to a thinner pen for accurate plot. So 0.3 is here. All right, 0.25 will be somewhere here. Okay, GS over 4, 0.25. GS over 9 is 0.11. So 0.1 is somewhere here. Okay, and GS over 16, 1 over 16 is, hang on, need to press my calculator. This one is 0.625. So here is 0.1, here is 0.5. So about half of it. So this is an older question. That's why the graph grids are, the boxes are big lah. But in newer questions, they will give you a better grid. All right. So we're going to join them together. So you just carefully plot out the points and make sure it passes through all the important key points on your plot in a smooth curve like this. All right. So this one, how many marks, you may ask? Well, this thing is actually 2 marks. Okay. 1 mark is for the shape. So M1 mark, I'm going to change this to red. 1 mark is for the shape. This is for the shape. And the actual one, we have to pass through a correct coordinates. Okay. So the coordinates here should be GS. This one here is GS over 4, which is 0.25 GS. Here is 0.11 GS. Here is 0.625 GS. So we are just estimating. So as long as it looks roughly correct, you will get 2 marks. All right. So this is a pretty straightforward sketch, and it's to prime your brain to think about part C. Okay. In part C, what are we looking at? We are looking at the gravitational force or the gravitational field between the Earth and the Moon. Wow, very interesting. There are 2 things here to look at. So let's read the question first. It says here, the Earth and the Moon may be considered to be spheres. Okay, so the Earth, Moon, okay, isolated in space with their masses concentrated at their centers. Okay, this is usual stuff, assuming that it's a point mass. Masses of the Earth and the Moon are given. Okay, sure. The radius of the Earth is RE, and the separations of the center of the Earth and the Moon is 60 RE. So the Earth and the Moon is 60 times the radius of the Earth apart. Okay, so that's the setup that we have. Let's continue with the question. Okay, part 1. Explain why there is a point, there's a point between the Earth and the Moon at which the gravitational field strength is 0. So if you think about it, let's say this is the line joining the center of mass of Earth and Moon. Let's say I take a random rock and put it here lah. So 2 things or 2 forces will be acting on the rock. Number 1, this rock will be attracted to Earth because Earth is like, bro, I want to be your friend. Please come here. This is gravitational field of the Earth. But also, it will be attracted to the Moon because, you know, Moon has mass and it's also attracting the rock towards it. So there's gravitational force of the Moon. So there will be a point where these 2 magnitude-wise will be the same. And then the rock is like, okay, lor, you pull me in one direction, Earth. You pull me in the other direction, Moon. I'm just going to chill here, man. You pull me on 2 sides, the forces will cancel out. All right. So please talk about how they are in opposite direction, because this one is a vector. So 2 points. First things first, we will say that the gravitational field, okay, the G fields of Earth and Moon are in opposite direction. So then you can say, since G gravitational field strength is a vector, there is a point where the resultant field, the resultant G, is 0. Because the magnitude is equal. The magnitudes are equal. Okay, so where are the marks? Number 1, you talk about how you know the gravitational fields are in opposite direction. Okay, this is M1 mark. And because G is a vector, this one is not not that, okay, fine, I'll delete this, not that important. You need to mention that the resultant is 0. So the term resultant is important. When the magnitudes are equal, this is A1. So they cancel out, something like this. Okay, so now in part 2, you are asked to determine the distance. All right, you're asked to find the distance in terms of RE from the center of the Earth at which the field strength is 0. So let's say this random point that I draw, or this random point, is where the field strength cancels out. So this field strength is supposed to be 0. But how do we know this one is 0? Well, so they want us to find in terms of RE from the center of the Earth. Yeah, from the center of the Earth. So from the center of the Earth is here. Let me switch color a bit. Center of the Earth is here. I want to measure from here all the way to here. How many RE? 1 RE, 2 RE, 10 RE, 50 RE, don't know, need to calculate. Okay, so let's just call this X. We want X in terms of RE. But good news, if we want to look for X, we will know what this value is, right? Here to here will be 60 RE minus X. Does that make sense? Okay, because the whole thing is RE. Now you may be thinking, Miss, why do you care about the distance of the moon from the position of the rock where the magnitude is the same? Well, my friends, I'm going to eventually use the equation G is gm over r squared, right? So here to here is the radius measured from the moon, our moon. And here to here is radius measured from the Earth. Let's say I call this RE. Okay? Not the same as this capital RE, which is the actual radius of the Earth. Okay? So we are going to measure the distance from the center here all the way to here. Okay? So that will be this. Because we want to know how strong is the field of the Earth at that particular point. Okay? How strong is the field of the Earth here? Wow, lag. Okay? So Earth, we will measure the distance from here all the way to here in our equation. Okay? And then for moon, we're going to measure distance from here to here. Okay? So now I'm going to start with the equation first. They will both have the same magnitude. So I can say gravitational field of the Earth, magnitude-wise, is equal to gravitational field strength of the moon. And then I can substitute G, mass of the Earth, divide by distance from the Earth square is equal to G, mass of the moon, divide by distance from the moon square. First thing you will notice is that the value of G we can cancel off, right? And then now you may be thinking, oh, can substitute? Okay, you chill first, you chill. If you look at the mass of the Earth, it is this prefix, right? And you look at the mass of the moon, is this prefix. So I'm thinking of taking two big numbers and dividing them so that I don't have I have a manageable number instead of cross multiplying. Okay, so what I'll do is I will move the masses so that they are together. Okay, so this is just a technique to make sure that I can simplify my calculation a bit easier. So I'll take mass of the Earth, divide mass of the moon. Okay, and this is over distance from the Earth square, distance from the moon square. Okay, so I can now substitute the mass of the Earth, which is okay, let me copy this, 6 times 10 to the power of 24. Okay, and moon would be 7 times 10 to the power of 22. 7.4 times 10 to the power of 22. Divide by, okay, radius of the Earth just now was X. We are looking for the distance measured from the Earth square. Okay, radius measured from the moon will be 60 radius of Earth minus X square. Okay, so in case you are confused, RE here is, here to here is RE. This distance here to here. Okay, this purple color arrow. Capital RE is here to here, radius of the Earth. Not the same thing. You want to call it something else to avoid confusion? Also can. All right. So I'm now looking for x in terms of RE. Okay, so I will put it in. Here is where sometimes people will think of, oh, I need to, open the square, a square minus 2ab minus b square. Please don't do that to yourself. You will encounter a very strange quadratic equation that you may need to solve. Now, of course, you can always still do it, still solve it, because we have our mighty one and only Casio, the calculator, but this is faster lah. So if you congregate this one on one side, divide by 7.4, E22, this will be 81 or 81.1. Okay, so I'm just going to write this as 81.08 lah, let's say. And this one I can put all the square together, right? X over 60 RE minus X square. So if I can square here, it means that I can square root here. So I bring the square over to square root. All right, so I will do that now. Let me, oh, my calculator crashed. Let me pull out the calculator again. So on one side, I will square root 81.08. Okay, so I'll get 9. Very nice. Okay, so 9 times, I cross multiply, 9 times 60 RE minus X is equal to X. We are looking for X. Okay, I'm going to continue here. When we look for X, we will open up the bracket. 9 times 60 is 540. RE minus 9X is equal to X. And then we combine all. 540 RE is equal to 10X. X will be equal to 54 RE. Okay, so this 54 is quite big, but it is to be expected, right? You are quite far away from the Earth. 54 RE. Okay, what I mean to say, I'm going to scroll up now, is that here to here is 54 RE. Meaning here to here, obviously not drawn to scale, will be 6 RE. About 10%. You'll be closer to the moon. Moon has a smaller mass. So for the fields to be comparable, I need to be closer to the smaller mass. All right. So makes sense. If you get something that is really small, then something is off. Okay, now the last part. On the axis, sketch a graph to show the variation of the gravitational field strength with position between the surface of the Earth and the surface of the moon. Okay, so I know one answer definitely. I know the resultant is 0 when the distance is 54 times the radius of the Earth. Okay, so basically I'm going to draw it very close to the moon, about 10%. So somewhere here. So I must pass through this point. I must cut the x-axis. All right. Then you may be thinking, wow, Miss, what shape? Just now you drew this shape. Gravitational field surface. It looks like this. If you remember, something like that. Right? So now we're going to have to draw this shape again. But because of the resultant field, okay, so we're going to draw, they say, between the surface of the Earth. So I'm going to start from the surface of the Earth, okay? Between the surface of the Earth to the surface of the moon. Okay, so you may be thinking, okay, I know. On the surface of the Earth, it is pretty close to our good old 9.81 because we know this already, ma. And then after that, this one will drop. Okay, so you're going to just decrease until it hits 0. Something like this, okay, to follow the shape. Then you might be thinking, what about the moon? What about the moon? If you measure from the moon, it will also follow the inverse square shape. So it's still a curve. But because when you're closer to the moon, the field strength of the moon will overtake. Okay, so let me go back up here and explain to you. if we go back here, let's say I take this point. Okay, maybe I choose a different color. Let's say I take this point. Okay, this point here. The gravitational field of the moon will be a lot stronger because we are now closer to the moon compared to gravitational field of the Earth. So moon is winning already. The resultant will flip direction. So now the resultant will be pointed here. Hang on, let me change color. Resultant will be pointed here. I draw a double-headed arrow, okay? If let's say here the resultant is 0, then if we move closer to this side, gravitational field strength of the Earth is maximum, or not maximum, is bigger than gravitational field strength of the moon. So you can see the moon is getting weaker and weaker as you travel further away. The arrows are getting shorter and shorter. Okay, whereas the purple arrow for Earth is getting longer and longer. So if you think about it, that means the resultant will favor Earth because you're closer to the Earth ma. So this is GE. So we will see, not GE, resultant, GR. I just call it too many R's already. I have two-headed arrow is resultant, you understand that, right? Okay, so if the resultant change direction, okay, it changes direction from this direction towards the Earth to towards the moon, it means that you have to flip the graph polarity. So I took this side as positive, meaning this side must be negative. Okay, so if I take one side as positive, then the other side will be negative. So right now I'm going to go back to the graph and draw this side as negative lah. It's not going to be very big. So actually, the moon's gravitational field is kind of small, 1/6. So if you want to draw very accurate, it should be 1/6 of this one. But you don't have, you don't have enough information to calculate that anyway. So as long as it's small, all right? So another option is to have your graph shape, okay, I'm going to draw a small one here, okay? Is to have your graph shape, basically do a reflection on the x-axis, yeah. So your graph will be like this and then like this. So for this one, you will take right as positive and left as negative. Doesn't matter, okay? So this is the shape. And where are our marks? Well, let's see. For the graph, if your G is equal to 0, I guess let me crop out the mark scheme for you. Okay. So this is the marks allocated. There we go. So G equal to 0, at least 2/3 distance of the moon. So that means this part is correct, lor. Okay. GE and GM in opposite direction. So opposite polarity, opposite sign, not polarity. Sign, opposite sign. Okay. So the sign here is for vector GE and GM. So here is GE at the surface of the Earth. This value here is GM. Okay, opposite direction. Correct curvature by eye. So I expect to see that sigmoid shape. Okay, and then GE here is bigger than this one. So it's just a rough sketch. If you want to be very particular, if you know it's 1/6, then you should scale it accordingly lah. But as long as you get this smooth curve or this one, is all acceptable. Okay, so that's it for this part of the question, the sketching. And when it comes to calculation, if you identify correctly this distance, okay, and you write the correct equation is 1 mark. So this is C1. Substitute everything correctly is C1. Final answer correct is A1. Standard stuff lah. Okay, so this is an old question. It's about the gravitational field strength between Earth and Moon. Okay, and remember that they are vectors, so they should be treated as vectors. If you move close to the Earth, the strength of the field strength of Earth will be stronger. Close to the moon, moon will be bigger. But there will be at the point in the middle where they cancel out. That will be the main idea for this question. All right, that's it. I'll see you in the next one. Bye-bye.